He is Chris Battershill, Professor of Marine Biology and Chair of the Coastal Science at University of Waikato. And I am willing to bet, yes, please give him a round of applause. I am also willing to bet that he is the only man that you have ever met who has a PhD in sponge gardens.
And proud of it.
And proud of it too, I like that. Firstly, Chris, what is a sea sponge?
A sea sponge, well, we have some here for you. Not those ones.
Okay.
You wanted me to bring those ones.
Okay.
But we have a couple of sea sponges here for you. They're the oldest living multicellular organism on the planet. Some 800 million years old is how long they've been around. And they really haven't changed all that much in that time. What they have developed, and that's the focus of our bit of a chat today, is some very, very clever chemistry. So some of them are spongy sponges, the ones that you have in your bathtub perhaps, particularly if in the Mediterranean. It's market worth about 40 million US dollars, by the way, per year. And the other one, this has just got full of collagen, very similar to our collagen actually, and they can be used for some medicinal purposes, wound healing and the like. At the other extreme are these, they're called siliceous sponges, and these are made of glass spicules, and this is a fantastic example. This one comes from a very deep area, the abyssal plains. And these sponges can generate glass at around -2 degrees C in the Antarctic. Imagine the temperature we need to make glass, and yet these things are doing it at very, very low temperatures. There's a clue there that we can pick up on in terms of making this sort of stuff. This one's particularly interesting because if you're able to look in the bottom of this, there's the remnants of 2 shrimps. I mean, you'll always get me to extend a story. And these 2 shrimps are trapped in there. It's also known as Venus's love basket. So hopefully they like each other. But they'll live in there from a very small age. They grow big enough that they just can't get out, and they are symbiotic with the sponge.
They are 100% trapped in there for life, aren't they? Pretty much.
Certainly
and death
are, yeah.
and eternity, really.
They certainly are.
So in terms of sea sponges, can you tell me a little bit more about them and why they are so special?
They're special because for us anyway, for the chemistry that they produce. They're enormously important for the environment because they can filter vast quantities of water. An average sponge will, in a little square meterage plot, would filter about 8 tonnes of water per day. And if you were a sponge garden, for instance, and we filled this entire room with water, and it had all of the bugs and particles and plankton in it, you would be able to vacate all of that, strip it all out of the water column in just under an hour if you're all sponges. So massive pumping machines. And in that time, sadly, you'd probably very soon be dead if we didn't replenish that water because you burn through the oxygen in that time as well. So they're like nuclear reactors. And while they're stripping that water out, they're garnering some of the stuff that they eat, particularly the bugs. And some people there, microbiologists, they like to look at little things, but they like big numbers. And this guy, Sogan and his team, they had a look at and estimated how many bugs, these are bacteria, microorganisms, are in seawater, and calculated 100 times a billion times a billion times a billion cells in seawater, and worked out that if you converted that to, if you filtered it all out and weighed it from the world's oceans, it would work out about 240 billion elephants worth of weight. Tauranga Harbour on a full tide is probably about 10 elephants worth in weight. And then if you go smaller still and you look at all the viruses out there, there's about 1 mil of seawater has about 50 million viruses in it. And not to be outdone, Curtis Suttle decided to work out if you stuck each little virus, it's just a little bit of chemistry really on a stick. If you stuck them end to end, he worked out how far into space the world's oceans worth of viruses would go, and he worked out it would be 60 galaxies. So the reason I tell you all of that is because all of these things are a big chemistry soup, and the sponges are taking advantage of it. And what they're doing is mixing their chemistry up, and that makes it interesting to us.
So whereabouts are we finding these sea sponges, and who's good at finding them?
They're found everywhere, from the intertidal down to the abyssal plains. They're found from the high tropics and all the way down to the poles, and we've looked everywhere for them. It transpires that humans are very good at finding them, particularly if they're looking for compounds of interest with a medicinal endpoint to them. But it transpires that many of the organisms out there that are trying to feed off these things also find them very easily and are quite selective, like fishes. They'll determine, for instance, based on bite rates and whether there's toxins in there, what colour sponge to eat in what order, so they don't get too much of the chemistry off them that might kill them.
They are in Tauranga Harbour?
They're certainly in Tauranga Harbour, and in a recent survey one of our students did, there were about 50 species of sponges found in Tauranga Harbour, and we came across a number that we know are very interesting in terms of some of the medicinal leads that they've generated. So it's a very diverse harbour, this one.
Here is the big question, and what we are leading to when we are talking about sea sponges. So we're not just two dudes talking about sea sponges. Why are they so important in drug research and implementation?
The reason is that in that time, that 800 million years, rather than developing legs like a lot of things did to run away from the enemies and to run away from being eaten, what they've developed is a very sophisticated chemistry. So they've been able to borrow some of the chemistry of the bugs and things around them, and they've turned that into a chemical weaponry, an arsenal, if you like, that they can deploy depending on what the situation is. And so this image that you saw up there just a moment ago, taken by a friend of mine, Libby Evans-Illich, is of a soft coral that is trying desperately to take over the rest of that real estate. The things that live on the seabed like to have territory and real estate, and they need to own it. And you can see there a little sea squirt sitting in the middle, defending its patch. And you can see that there's nothing really much in it. So this is a soft coral situation on a rock, and if you go under the kelp, you'll see that even around here. And so you've got water washing over that, so anything that little sea squirt is starting to generate is enormously potent because it's diluted really quickly. And if you start to look in on the edge of the soft coral surrounding it, you'll see that it's actually looking quite healthy. There's no sign of death or anything. So the compounds that little sea squirt is secreting isn't killing cells, rather it's getting into those cells and it's switching them off. Now when you think you're looking for an anti-tumour active compound, what do you want? You want something that's enormously potent, you want something that gets into cells and only aberrant cells, cells which aren't healthy, and ideally you want it to be able to switch those cells off so that your natural immune system can come and clean it up, not to be just a cytotoxin, as they say. And that's what these sorts of compounds do. They're designed to do that. But furthermore, they're smarter than that because it seems that these organisms can sense what their neighbour is. And they don't want to just kill off neighbours willy-nilly, because you never know when something's going to come in and take over your space. It might be smarter than you, than you have chemistry to defend it for. So what they do is develop a chemistry that they know what their neighbours are. So it's very, very smart.
Go the sea sponge.
Go the lowly sea sponge.
That's amazing. So not just sea sponges, there is a correlation when it comes to sea organisms and your cell phone as well?
That's correct, yeah. So other organisms, instead of working out some very smart, what they call organic chemistry, so molecules that are bioactive, they accumulate some of the toxins that might be out there. Vanadium is one. It's a rare earth element and enormously important for cell phones. And sea squirts in particular can accumulate vanadium out of the water column, and some vanadium and chromium, arsenic and things can be pollutants. They'll accumulate those compounds 10 million times higher than the water column. So they're sequestering that stuff, they're grabbing it in there for their own defence. And the sea squirts in particular get the stuff into specialist cells which have a pH of 2, more strong than your car battery. It's full of acid, and so they keep these things in there. Other organisms have learnt to use that. Nudibranchs, for instance, the little sea slugs, they can come and suck this sort of stuff, and they move that toxin into their skin surfaces. So nothing likes to eat them either.
Mate, give me an example, because we've heard about the great immune things that the sea sponges do. Give me an example of some of the drugs that have been derived from a sea sponge that are currently in use and some that are being looked at the moment.
Yeah, I'll give you two examples from New Zealand. We've actually done extremely well, it's not well known, in the international search for drug leads from the marine environment. There's been an international program going on for many years, and New Zealand's done exceptionally well. There is a drug out there, it's called halivin, and it comes from a sponge, which was aptly known yellow slimy, collected off the Kaikoura coastline right on the edge of the canyon. Whether that sponge population is there now, we think maybe not, since the earthquakes. But that sponge, and alongside another one that was collected initially in Tauranga Harbour, and we found the same species here in Tauranga Harbour. Both of them are the sorts of sponges that grow over other things. And initially, the chemistry from them was identified as having immunosuppressive activity. And when you think about it, as soon as you put yourself in a sponge's place on the sea floor, you think, well, that makes a lot of sense. If you're about to grow over something, you want to be able to switch off its antagonistic response, because they have also chemical weapons. So these sponges have an ability to be able to switch off those sorts of cells. And that's what they do. And it's probably not surprising then that they've got applications as anti-tumour actives. The Kaikoura sponge and the compound it's generated is now known as halivin. It's a drug that's out there. It's a late-phase breast cancer active. And what it does is it switches off the tumour cells from dividing. Very much the same way as I described for the soft coral and the sea squirt. And that's why they're exciting.
Go the sea sponge. Again, that's amazing. That's from waters in here in New Zealand. That is so cool. So give me a snapshot of how you got involved and enhanced that field of aquaculture.
I've always been interested in things of nature, and don't listen to this. I've got a boss in the room here, and my students are out there somewhere. I was a very poor student. In my early days at primary school in South Auckland, Mangere East, I used to cut school and go wade around in the creek and just look at stuff. That was really interesting. And that's why I got interested in science. But I was also interested in medicine at the same time. But the call of the sea was too great, so I ended up becoming a marine biologist. And initially looked at oil pollution, funded by Shell, BP and Todd in those days of the Think Big projects in Taranaki. And from that point, I learned how resilient marine organisms were and how they actually used some of these pollutants for their own defence. That led me into a program that was initially funded for my doctorate research by Roche. And since then, I was engaged with both national and international programs for looking at drug leads from the sea. So we were able to dive everywhere. It was fantastic.
Wow. And not just medical as well, veterinary and agriculture, is that right?
That's right, yes, because we found that in the search for medicinal leads of human relevance, things like Pseudomonas, which is a lung disease, an autoimmune disease. You suddenly realise, of course, when you recognise that PSA is a Pseudomonas bug, right, a pathogen. And we recognised that we could map over the information we were getting from the drug discovery programs into other sectors like agriculture, and indeed that's what we've done. And we put up, for instance, to some of the companies around here, a challenge really. We think we can help you find some anti-pathogenic compounds, some things that might be of use to PSA, for instance, in the kiwi fruit industry, if we map over what we understand from the medicinal industry. And we did that, and there's been quite some considerable success in around that.
Some of those in the kiwi fruit industry in this room would like to say, could you do it a little quicker?
Yeah.
That would be fantastic. Thank you.
It's happening quickly.
So where have you been diving? I find this very interesting. Where have you been diving for sea sponges?
Fortunately, I've had a blessed career, I have to say. I've been able to dive all the way from the high tropics, all around tropical Australia, the South Pacific, and then down to the Antarctic. Some of the best places for me have been in this country, Tahua, Mare Island, just offshore, Astrolabe Reef, Otaiti, where Rena hit, of course, Poor Knights Islands. But the best places for me to go and hunt aren't necessarily the best places to find the medicinal leads. So I've dived some of the other places as well in the hunt for those. And the best places to find medicinal leads are sewage outfalls. So we rosin up very carefully. Every single orifice is crammed full of Vicks Vapor Rub, and just to make sure it's sealed. And
like every single orifice? Sorry, go on.
But that's where you find them. And surprisingly, you have sponges and other organisms responding to human sewage outfalls. And if you're interested in a herpes simplex antiviral or a poliovirus antagonist, that's where you go and look. Now, we've learnt from that experience to not necessarily go to those places anymore. Once again, if you look at nature, that's where the clues are, if you pick up on that. And if I cut back to the Kaikoura story and the yellow slimy sponge, the organisms out there have found these things already. When we dumped one of the trawls on the deck, this was from deep water, about 100 metres, and the yellow slimy sponge was in there amongst all sorts of things. There were a bunch of camouflage crabs in there also. And we noticed that they were quickly getting rid of the seaweed and stuff that they had on them and then grabbing this piece of yellow sponge and shoving it on their shells. They knew straight away that that yellow slimy sponge in that trawl basket was the most nasty compound bearing sponge there is, and so they were covering itself for its own defence. So I've learnt now not to go to sewage outfalls. We just grab camouflage crabs and let
them do the work. Yeah, totally. Let them do that work. So if you can just take us through reasonably quickly how the process of getting a sea sponge from seabed to human use actually works in terms of that drug company process, because it's not just here's a sea sponge, let's eat it.
It's a very, very challenging process, and particularly from marine natural products. 75% of the drugs that we all use today and the antibiotics come from nature. Aspirin from willow bark, for instance. There are heart therapies that come from digitalis foxglove, and many of them are terrestrial. Many of them are still actually produced by agriculture, funnily enough. The sea represents by far the greatest diversity of species, and therefore the biggest diversity of chemistry that you can imagine. So most of that's out there. But the problem is being able to supply it. So to generate 1 gram of helicondrin B, which led to the Halavan drug, for instance, it takes a ton of sponge. Now that sounds like a lot of sponge. Most of it's wet, of course. 90% of it's wet, but it's a lot. And it was that perception of supply that is hindering drug industries from tracking that through its preclinical trials, 3 phases of clinical trials, and then 4th and 5th phases of marketing and development. It's cost the drug companies between $750 million to $1 billion per year to get any one drug through these days. So all the time they're weighing up this thing from the sea, not quite sure if we can produce it in enough supply, with a synthetic that they can and that they can generate in the lab. So that's the trick to it.
So we need to make sure that we've got lots of sponges and lots of opportunity to look at them and see whether they work. But our problem is, because we're just scratching the surface, is that those sponges are currently being destroyed. How is that happening?
Yeah, sadly, in our estimation, about 1/3 of the sponge gardens, these are the reefs that have sponges on them, in and around New Zealand and in probably most of the countries in the world, have suffered because of primarily sedimentation, unsustainable trawling practices in the past, where trawlers would use what they call tickler trains to mow down sponge-type gardens so that the nets wouldn't get snagged, things like that. But it's sediments primarily. Every time you fly around this country, or anywhere actually, you'll see muddy rivers spilling out into the coasts. One river in this country, for instance, will produce about 35 million tonnes of sediment every single year, just one river. When you work out what that looks like, it's about 80 farms worth of topsoil going out that river. So it only takes a millimetre of that sediment to smother some of these sponge communities. They don't deal with sediments very well. And so we're losing that diversity very, very quickly. And the significance of that, of course, is that we're losing the opportunity to find these new leads for potentially new treatments that we might need to consider in future generations.
So what can we do to turn it around?
What we need to do to turn around is act a bit more conservatively. This is certainly happening in this country with restoration of land, planting riparian strips, trying to keep the soil absolutely on the land, which is in everyone's interests. And also more sustainable fishing practices, of course. So pair trawling, that bottom trawling, is now being limited quite significantly in this country and others. So it's being mindful that, we're looking at a marine environment that is suffering, some places, death by 1,000 cuts because we've got warming oceans, stronger storms and the like. So the conservation, hopefully I've given you here that the idea that conservation actually has some other benefits in terms of some of the pharmacopoeia or the medicine store, if you like, of the future that lies beneath us.
Sea sponge farms as well, right?
Absolutely, and in fact that's one of the ways we generated the ton of sponge we needed to progress the clinical trials for the Halovan compound. It was to aquaculture them.
Let's finish with what I think is one of the best pictures I've seen in a while. Tell me about the dolphin in this picture.
This image is one of my favourite in the world, and sorry for the grainy one underneath. That was sent to me many years ago, and it's grainy because it sat in the tropics for a little bit of time, and it's got a bit of mould on it. There might be something interesting in the mould too. But it was sent of a
You're like
dolphin.
the only guy who would ever think that as well.
Yeah.
I like that. I love that.
We're a bio-discoverer.
Yeah, go on.
So it was sent to me by colleagues in Western Australia, and who noticed these dolphins swimming around with sponges on their noses. The sponge is called echinodictyon, and we actually know now that it's quite bioactive. It's full of all sorts of interesting alkaloids and things. And of course, when you get an image like that, being a scientist, you sort of think, well, what are our hypotheses going to look like? You know, what do we think's going on here? And three things come to mind. One is that the dolphin's just playing with it. You know, here's an interesting shaped sponge. It fits on my nose. I'm going to swim around for a while. Secondly, it's using it like a glove, because we know these dolphins get down the bottom, they snuffle around the rocks and coral bommies to scare up crabs, and it's a protection. But the third hypothesis, of course, is that it's getting some medicinal content out of that sponge, and we know now that is a high possibility. Also, in more recent times, the folks who sent these photos over have indicated that it's mostly pregnant female dolphins that do this. So it might be getting something out of that sponge that is rushing through its system, fusing parasites maybe, who knows. The point being that you need the dolphin and the sponge together in a combined environmental system that is intact to be able to not only have them present for that diversity, but also so we can pick up on some of the leads that this dolphin is discovering that might be of use to us. And it's a message that the famous Dr. Sylvia Earle, a famous marine conservation, has said that you need these intact, integrated habitats over large scales to be in place for us to benefit into the future.
That or it's just getting high.
It could be getting high because, yes, there are alkaloids in there, and we haven't yet done the taste test, but
all right.
That's to come.
Ladies and gentlemen, you need to go home and you need to tell your kids to study dolphins and sea sponges. It just may save your life or theirs. Ladies and gentlemen, Professor Chris Battershill.
Good.